My theme this morning is Einstein, Eddington, and the Eclipse expeditions of 1919. And I wish to thank two colleagues, Heino Volker and Peter Coles, for some images which I'm using today. Now, of course, the fundamental foundations of Newtonian dynamics was developed by Sir Isaac Newton himself, who may have needed a haircut from time to time. I do not know if such a hairstyle would have been welcomed on campuses at this epoch, but it was the brain he possessed which attracted his attention and our attention, and not his hairstyle. Newton in the Principia, which I think I've examined at the University of Cambridge, says, "The supreme God is a being eternal, infinite, absolutely perfect, who endures forever and is everywhere present, and by existing always and everywhere, he constitutes time and space." But according to Newton, space and time were completely flat. You had the motion of particles, you had the motion of projectiles in space and in time, but it never entered the mind of Sir Isaac Newton that space and time were inextricably linked. Now, it takes an NJB to really move things forward from time to time. And does anyone know what an NJB is who heard me on the Austin, Texas ranch? A nice Jewish boy. If you look at the Nobel laureates, lots of them are NJBs or NJGs. Huh? Nice Jewish boy. And in this case, Albert Einstein, he came up with a fascinating theory, is that whereas in Newtonian dynamics, light could travel simply in the shortest path between 2 points, space was essentially flat. We call it Minkowski space-time. In general relativity, Einstein came up with the idea that space-time is curved. It's remarkable that space-time, so glad this lady's taken a picture. I mean, it makes me feel good that I didn't just put this all up and nobody's taken some notice of it. And you see like a rubber membrane, and you put, say, a marble of iron in the middle, and it causes the rubber membrane to sag. We call it the curvature of space and of time. Now, I want to explain this because this is very much to do with what's happening today, is the deflection of light past the sun as seen by a cluster of stars behind the sun. So here we have the Hyades star cluster, which is around 160 light years, I believe, from us. And you can see that if the sun were not there, we take a photograph, the stars appear closer together. The stars appear closer together. But if we photograph that same cluster during a total solar eclipse, the same stars seem to move further away from each other, and that's because of the deflection of light past the sun. You see, if you go to the right-hand ray and you project upwards, the separation between the stars is increased because light is deflected past the sun. But if you take a picture of the Hyades, say 6 months later, they'll be a lot closer together. Because Einstein predicted that the sun would bend space and time, in direct contradiction to so many earlier scholars. And here I am. I must show you a little picture. I haven't got jokes as good as Jeff. But anyway, there I was around 19 years old. And my hairstyle was dreadful. But it wasn't as bad as Newton's. And there I'm lecturing on active and conformally active symmetries in metrically automorphic spacetimes, admitting linear collineations. The math is a little rough if you're 19 years old. When you get 30, it gets a lot easier. But at that stage in my career, I was greatly challenged by the beauty of general relativity. And here you see we had a visit by Martin Schmidt, whom you would know well from Celtic days, who discovered quasars and intense gravitational force fields. But again, we're talking about these things, and my hair looks like a rebellious octopus staging a protest against shampoo. These, ladies and gentlemen, were the days of the Beatles, and I tried to follow suit, but I was never as popular or as successful. So the deflection of light by a mass such as the sun goes back to Newton, to Cavendish, to von Solder, who published a calculation of 0.84 seconds of arc. A second of arc is just 1/3600th of 1 degree. Then Einstein comes along. And who was going to be right? There were experimental physicists, astronomers who tried to check out, is Einstein right? Was Newton right? And some of these include Findlay-Freundlich. Einstein finds an observer assistant, Findlay-Freundlich. Then there was also Campbell, director at Lick, who races with Findlay-Freundlich to disprove Einstein or prove him. But there were problems. In 1914, there was a total eclipse of the sun, but war broke out the week of the eclipse. Campbell's equipment in Russia was impounded, and Findlay-Freundlich was arrested in Turkey, and it's difficult to prove the deflection of light past the sun in prison. So then in 1918, Campbell was clouded out in Washington State. So there was a famous eclipse in 1919. We celebrated the 100th year in 2019. And the path is in green. It swept over the northern part of South America, especially Brazil, and then it went over a very special island towards the west coast of Africa. You see Albert Einstein at upper left, and you see Sir Arthur Eddington. How many have seen the movie Eddington-Einstein? It's an incredible movie to actually watch. And so at the forefront of all of this, the key experimentalist, of course, a famous professor of general relativity. I think he was once asked how many people understood general relativity, and he said something like 2. Einstein was one, and he was the other one. So at that stage, not too many people understood general relativity terribly well, but Eddington certainly was extremely well versed in GR. Eddington, I remember Eddington sitting with Einstein on a famous bench, one of the universities, I think, in the UK, maybe it was at Princeton. But anyway, he was the central figure to go out and see whether Einstein was right or whether Einstein was wrong. And so again, the path of totality is seen at left. Some of the astronomers were Dyson and then, of course, Eddington. And then you can start seeing that the stars apparently move. But the question was, how much did they move? What was the deflection of starlight-like behind the sun. And so they had to choose a suitable locale, and the locale they chose was the northern of the two islands, the Principe Island off the Gulf of Guinea, in on the west coast of Africa, and you've got Sao Tome on the in the southern swath of that slide. So covered in plantations. Eddington looked at several possibilities. The path of totality crossed these islands, and he decided on the locale of a place called Roca Sunday, Sundee, a Portuguese colonial plantation in the north of the island, and he sets up his telescopes there. Now, the reason I'm showing you these slides very quickly is that you can see there's a tremendous amount of cloud over the island. Tremendous amount of cloud. Just watch the cloud cover. Wherever you look, that's the local airport relatively recently. And again, very, very thick cloud cover. Again, a journey which didn't end too well, but nevertheless, very, very thick cloud cover. That was Eddington's problem over and over again, was there was the densest of cloud cover. And there is circled Roca Sunday, from which these great experiments were to be made. Again, much cloud, but some buildings, as you can see, cloud yet again, folk playing. This was in 2019. And this was quite interesting because this was a tennis court at the time of the eclipse. And again, it goes to show Campo de Tennis, of course, greatly dilapidated today. But if you look up again, there's no blue skies. So you can see that cloud was Eddington's greatest problem. Imagine putting up all this equipment and it appears to be totally cloudy. So this is what the telescopes look like. This is the one in Brazil, the observing site on a race course at Sobral in Brazil. And here are some facts and figures. The funding was not extensive, £100 for the equipment, that's all. £100 for the equipment, 1919, and £1,000 for travel and labor costs. They had two telescopes, two astrographic telescopes, 8 inches. One from the Oxford area went to the island of Principe, and the other Sobral from Greenwich, that was in Brazil, the telescope there. And all were equipped with celiostats to take the incident sunlight and reflect it into these telescopes. And they were all mounted in stainless steel tubes. Now, there was a moment in time on the Principe Islands when the clouds opened up. There was just some moments when the clouds opened up, and they secured that. Now, this is an incredible image. This is a solar prominence from the Principe, 1919. The exposure time is, and it says 10 seconds through cloud. That's why I was so encouraged when Hugh said, don't look down necessarily today because of cloud, because this is taken through cloud, and it's the most incredible image. And that's a close-up measuring the stellar deflections. Again, I've explained that these are radial displacement of stars due to the deflection of light past the sun. But how much would the deflection be? So these are some of the plates which were used to measure the deflections of the Hyades star cluster. This was an acetate copy of one of the plates. You know, when I worked in astronomy in terms of the darkroom, and Hugh would remember this, my glass negatives were this big. You know, people speak of 35 millimeter negatives. My negatives were on glass plates this big, and they were about 1 millimeter thick. They're very, very difficult to develop. I spent 4 years in a photographic darkroom developing photographic plates of that nature. And again, the deflections. Now, we've actually taken one of the plates and we've restored them. So we've scanned one of the plates digitally, and we've removed all noise. We've removed all artifacts. We've included image restoration. And I wanted to see here, this is what the image actually shows today. Stunning details in the solar corona, giant prominences, and of course the stars. So let's go here now, and that's the one. It's a magnificent image, but that's what the image would have looked like using technology today. Anyway, there's data analysis, and I don't want to go into all of this, the math, but the point was Einstein came out to be the winner. So the results. The results are Eddington was nearly rained out. Through cloud, hopeful. Cromwell says the Eclipse splendid from Brazil. But the idea was that Einstein's magical theory of relativity, the idea that space and time are inextricably and forever linked, proved to be correct. And the world press went mad. There you can see Newton's results and the Einstein, the results fitting so magnificently. And so Lawrence sends a little telegram to Einstein basically saying, you've done it. You've done something nobody ever thought of. General relativity is the winner and not Newtonian dynamics in the presence of gravitational force fields. All right, and so new theory of the universe, Newtonian ideas overthrown. On the right, Einstein's theory triumphs. There we are. This is extraordinary. The New York Times, November 1919, hails this as one of the greatest of human achievements. I mean, if that doesn't excite you, you're dead. You need to apply for a job in a funeral parlor. I mean, this is the stuff that NJBs love to do. This is one of the greatest of human achievements. Come on. I still am amazed at the genius of a little NJB, Albert Einstein. Einstein became the most famous scientist ever, not because of a special and general relativity, but because of the eclipse. Because of the eclipse. And there's a picture around the time of Albert Einstein actually, you could just see in deep, deep thought. This was very interesting. This one says in the Washington Times that it's the greatest discovery in history. But notice what it says on the left. Eclipse shows space is limited, the greatest discovery in history. And the newspapers were full of this, from London to Sir Oliver Lodge's comments and much besides. So that shows you the importance of solar eclipses. It all happened during the eclipse of the sun, that the deflection of light was all verified. Now, I want to show you the extreme deflection of light. The extreme deflection of light. And that's the deflection of light past a black hole and around a black hole. Now, the reason I've chosen black holes is that there you have an extreme example. The gravitational force field can be a lot larger than the sun. But I want to tell you something. There was an error somewhere mentioned by my students years ago. Black holes are dense. That's not true. If you've got a supermassive black hole, as you cross the event horizon, the density can be less than that of air. It's true. You work it out. Density is mass over volume, volume 4/3 pi r cubed, and the mass scales R is proportional to m, so you get the density at the ergosphere is 1 over m squared. So for a supermassive black hole, the density is less than that of air. That's why the pass rate at my students was 10%. But anyway, a friend of mine, Heino Falker, allowed me to show you some images, some of his images from a black hole and another galaxy. So this is incredible. This is a telescope essentially the size of the Earth. Can you believe that? A telescope the size of the Earth. What we're doing is we're using very long baseline interferometry, and we are looking at telescopes from around the world. We've got one in Greenland, the Greenland Large Telescope. We've got one in the South Pole Telescope. We've got one in France, New Emma. You've got the James Clerk Maxwell Telescope, and so on and so on. So there's a collection of telescopes, and when they collect data all at once, you've essentially got a telescope, not the size like this or the size like the James Webb, but you've got a telescope the size of the Earth. It's called Very Long Baseline Interferometry. So there's some of the acronyms which I've put up. The James Clerk Maxwell Telescope, JCMT, the South Pole Telescope, SPT, the Submillimeter Array, SMA. You see, take the Submillimeter Array, for example. You see, it's a whole array of telescopes in the Atacama Desert in Chile. But they all act as one dish. And when you combine this with the data from all over the world, you get a telescope essentially the diameter of the Earth, which is extraordinary. So this is an image in optical light, but now we're going to start imaging in radio frequencies. So let's see what happens. Okay, so now watch. There's a black hole. It may be a Schwarzschild black hole, maybe a Kerr-Newman black hole, and you and I will be delighted to answer questions differentiating the two, not now, but this afternoon. So there we go. So you've got light bending to an extreme degree, far more extreme than the light bending around the sun, around these black holes. So there you've got light curving in. And the idea is black holes need not only be black holes can also be white. Hawking proved that many black holes can actually be white due to what we call quantum mechanical tunneling. And I'll be happy to answer that, but not now, in question time. Otherwise, you'll miss the eclipse. All right, so here we're going to a galaxy Messier 87. Giant radio lobes, huge giant radio lobes, larger than the Milky Way on each side. Just huge giant lobes of gas. And we're going to look at the gas moving around in the accretion disk of the black hole. So here you've got gas moving in towards the center of Messier 87. Just let me work this out. 20 megaparsecs, so that's around 60 million light years. Yeah, so here you have some of the collaborators from around the world, you know, and you can see that there are collaborators from Mexico, from Hawaii, from the South Pole. Now, how much data is being collected with all these telescopes the size of the Earth. Around 6 petabytes. That's the equivalent of storing MP3 audios for 6,000 years. That's equivalent of storing typical MP3 audios for 5,000 to 6,000 years, depending on the length of the audio. A petabyte is, of course, 10 to the 9 megabytes. So you can't transfer this, even if you've got good Wi-Fi at Camp Buckner. You'll sit forever. You'll sit forever, and you'll be buried, and you'll die, and you'll be buried, and you'll die, and you'll be buried, and you'll die, and the data wouldn't even have transmitted. A petabyte. This is 6 petabytes. So what we had to do was fly the hard drives to a central locale. It's the only way one could cope with so much data, is you actually flew the hard drives along to some labs, and then they were analyzed. But extraordinary amounts of data involved here. So the Event Horizon Telescope, you can see the Earth rotating over there, and you can see them coming into view. We're starting to synthesize data from the different telescopes, from Hawaii to the South Pole. I'm very grateful I'm not in charge of the telescope at the South Pole. And then, even though I keep on taking trips to Norway to see the aurora, that's quite different. That's spending months down in the South Pole. Okay, so we can conduct simulations. This is interesting. We can actually conduct simulations of what the images should look like, and then we can test what they actually look like. You've got a convergence of simulations and of observations. And that's right at the heart of our galaxy. That's right at the heart of our galaxy, Sagittarius A star. You've got stars right at the very heart of our galaxy, which are moving around the black hole at incredible velocities. I mean, that is an incredible zoom from the Milky Way galaxy, 100,000 light years across, right towards the center, and then right towards the actual black hole itself. Watch this one. So this is data, radio data. We're going in with radio telescopes now. And there you have 6 petabytes of data. That's the first image ever of a black hole at the center of the Milky Way. That's the first image ever, 6 petabytes worth of data, showing you the deflection of light, just like was predicted at the eclipse in 1919, but here on scales which you can barely dream possible. And now, something very interesting. We've actually been able to image the shadow of a black hole. So right. There's a model prediction at left, and there's the galaxy Messier 87 I showed you. That's the black hole at the center of it, 6 petabytes around. And then our Milky Way galaxy, the black hole at its center, Sagittarius A star. Why am I so excited to be director of Reasons to Believe Africa? Because I got 2 great friends, Hugh and Kathy Ross. And we've been working together, Hugh, since when? 1983. I mean, it's just been awesome. It's based on a relationship of love and of trust and of supporting one another, and he's been such a great source of encouragement to Liz and myself. But Hugh, we could never have dreamt that in our lifetime we would have images like this of shadows of black holes. These are not only the black holes, but these are shadows of the black holes. So you've got accretion disks around a black hole, and then of course the black hole blocks out starlight behind it, and it actually causes fluxes to dip. You can see a rise in intensity, and then a fall in the shadow, and then a rise in intensity. I mean, this is the stuff that not even science fiction was made of 10 years ago, to image the shadows, the actual shadows of black holes. This gives you the rotation period here, 12 days and 12 minutes. So that the one is spinning around very, very quickly indeed. Let me just pick it up on my machine. So those are very, very fast rotation speeds indeed, 12 days and 12 minutes. That was a paper I wrote when I was 19 on all of this, but of course it predated. You know, we didn't have the telescopes to actually look at this carefully. But I was so grateful that the late Alan Sandage said he read this paper and he was so encouraged that it covered such a diversity of topics in those very early days. That was written in 1973. I wrote that paper when I was 19. So it was predating so much of what we have today from an observational point of view. So there's one coming in Africa, the Africa Millimeter Telescope, the first African millimeter telescope, 15 meters across. It'll look at black holes, and it's being constructed in Namibia. And in fact, I've been invited to Namibia, Hugh, I think it is in June, somewhere around there. So imagine, reasons to believe, Africa. I think this is cool. Heading up to Namibia, and with the site of the next one. And you can see the funding there, millions and millions of euros. I want to end off with this. It's a famous, famous image. What are all those, what's this? The orange lines are called null geodesics, the path of light around a distant cluster of galaxies. And if you've got a galaxy in the background and the light travels near a foreground cluster, again, as in the eclipse of 1919, the light is deflected, and you should see gravitational arcs. Those are images of the distant galaxy everywhere. That's exactly what we find. That's exactly what we find, is all those orange arcs are gravitational. They are proofs of the deflection of light past a foreground cluster of galaxies. If you took a spectrum of each one of those orange arcs, they'd be identical, because the light is the same source. The light is the same. So it doesn't matter where you put a spectroscope on those, the light is exactly the same source, being the background galaxy. So much has happened since the eclipse of 1919, but what's very clear is that general relativity has not only proved to be the winner, but general relativity shows the mind of true genius. It shows the juxtaposition of a man who fled Nazi Germany, the harshest of conditions, and who dreamt up theories which go beyond the human mind, as it were. Theories of curvature of space-time, theories of Riemannian space-times, theories of Minkowski time, theories which really make the mind boggle. And his books and books are written about this, and Hugh writes about this so eloquently, and others, Jeff and so forth. We stand here at an amazing epoch, Hugh, in which theory matches observation. And observation affirms the Bible. That's what I love about this. There's a harmony. And that's the reason for reasons to believe, US. That's the reason for our global partner, reasons to believe APAC, and reasons to believe Africa. May the heart of Africa, from South Africa to Namibia, to Uganda and further afield, but especially Namibia now, be greatly energized to see the harmony, not only between black hole observations and black holes theory, but I want to speak to school children too about the harmony between in the beginning God said, let there be light, and there was light. My time is up. And I thank you.